If we look at our third example, in the third example, same sort of process. Are there any values of x that we can't have? Well, actually no, there is no value of x that's going to make this denominator equal to 0, so we can have any value of x. That's a good thing. Here's a tactic that you might like to use perhaps in dealing with this. This 1 at the front, all that's going to do is take whatever that curve is that we've got in here, which is, you know, the interesting part of the whole curve. That 1, all that does is shift the whole curve up 1 unit. So you know what, it might be helpful for us just to consider what we would have if we had y equals x on x squared plus 1. Consider this one first, and then once we've considered that, when it comes to sketching it, just realise that all our important information like our asymptotes, our horizontal asymptotes, and where the curve lies, will all be shifted up 1 unit. So again, if we look at this, there's no values of x that x cannot equal. X can have any value we like. There's no problems with that. So now let's have a look at the intercepts. Right, so for the intercepts, we'll go the x-intercept first, which means y equals 0. So 0 is equal to x on x squared plus 1. And very clearly, if I had a value of x equals 0, then the numerator will be 0. And so this whole function will equal 0. So when x equals 0, that is when we're going to have an x-intercept. So at the point where x equals 0, y equals 0, so our x-intercept is at this point right here. Now, we could follow through and actually go through the whole argument for what happens when, for the y-intercept, but actually, you can already see where the y-intercept is. It's hidden right in this coordinate right there. The y-intercept occurs when x equals 0, and when x equals 0, y equals 0. So this part here, that's actually called the origin. So this curve is going to go through the origin. That's where it's going to go through. So we've found out what our x and y intercepts are. Right, that's for the intercepts. They take place concurrently at the one spot. Okay, and now let's have a look at this and let's see what happens to this function as x becomes very, very large. And from what we've done before on limits, the limit, we should be able to see now that the limit as x approaches infinity has an infinite value, then the limit of this function will of x on x squared plus 1. Well, x is getting very big, but in the numerator, but in the denominator, it's getting very big much, much faster because it's a squared term. So this whole thing will have a limit of 0. It'll be a large number over an extremely large number, and the extremely large number wins out, so it's going to have a limit of 0. However, what's important to notice is that if we're going on this positive side here, if we look at our axes, and we're looking at the x-axis from the positive side, so we'll draw ourselves a set of axes. We've got this important piece of information right now, which tells us that the curve at this stage is going through that point 0, 0, as far as these, this blue analysis is concerned. We've got to come back and look at the original function in a minute and consider what this plus 1 is going to do, but for the moment, the blue analysis, it goes through that, the origin 1, 1, 0, 0, sorry. And if we're looking at all the values that are positive for x, that means we'll have a positive x in the numerator, and the value in the denominator is always going to be positive because the value in the denominator has an x squared, so that's always going to be positive. And that means this curve must approach the x-axis from the positive side of the y region. Okay, up here, this is approaching it from above. It's approaching the x-axis from above, is the terminology I was looking for. It approaches the x-axis from above. Right, what happens though when we look at the limit as x approaches negative infinity? From negative infinity of this expression, well, you know what? If x is negative, so all these negative values of x, that means the numerator is going to be negative everywhere. So it's always going to be negative there. But if x is negative, and then you square x, it's got to be positive. So the denominator is always going to be positive. And a negative number divided by a positive number gives you a negative. So this approaches the x-axis from below. Over this side, it approaches it from above. Over this side, it approaches it from below. And if we plotted lots and lots of little points, what we would find is that this function would look like that. Now, you know what? We could actually have a look at this and see it looks like it's an odd function. So let's double check to see if it is odd. So for odd functions, that means negative function f of x is equal to function f of minus x. Okay, that's what happens for odd functions. So we've got function f of x is equal to x on x squared plus 1. So negative function f of x will be equal to minus x on x squared plus 1. Alrighty, and now let's have a look at what's function f of minus x. Well, that would be minus x on minus x squared plus 1, which equals minus x, and when that's squared, we'll have just a positive x squared plus 1. And you know what? This here is exactly the same as that there, which means that this condition is met. It means that this is actually an odd function. So looking for odd and even functions can also give you an idea of what a curve may look like. Some of you will be upset that I've said we've got a limit here and that the limit approaches 0, yet we're finding that the line actually crosses over right here. It crosses over the line y equals 0, or the x-axis. These limits only deal with what's happening to the curve when it gets extremely negative or when it gets extremely positive. Those two limits there are only dealing for extremely large values of x. What happens right in close to the origin is actually a separate kind of dynamic that we've got to look at. And so we can actually, close to this part, we can actually cross over the origin. Now, as I said, all of this blue analysis is purely for that part of the function, but we've got a plus 1 here. So let's actually put the plus 1, because we don't want to go anywhere without our plus 1. And with this plus 1, we'll have, there's our x-axis, our y-axis, and everything just gets shifted up 1. So that was originally at the origin, 0, 0. We're adding 1 to everything, so it's moved up to here. So it's plus 1. So, and that's where it goes through there. And the curve is going to actually have the line y equals 1 as its asymptote, but it will have the same basic shape. It's going to come up like this, down, and like this. And you'll notice I was very careful not to let this curve cross the x-axis. Okay, it doesn't cross the x-axis because what we found is there is no value of x that we can put into this function. It will never equal minus 1. So that means it will never actually cross the x-axis. And that comes from an analysis of this part here. In order for this curve to touch the x-axis, this part of the function would have to be equal to minus 1.